Reality might be branching every time you make a choice. We are about to explore 30 theoretical journeys through alternate dimensions, a voyage that will fundamentally alter how you perceive existence itself. This journey will grant you a completely new lens through which to view the cosmos and your place within it. We will uncover if our universe is a holographic projection and what happens when countless versions of you split into parallel worlds. What single question about reality do you hope these dimensions can answer? Every choice you have ever made has spawned a universe where a different version of you lives a different life. This is the heart of the first theoretical journey, the many worlds interpretation of quantum mechanics. It began not as science fiction, but in the rigorous mathematics of a graduate student named Hugh Everett in 1957. His radical thesis proposed a stunning idea. Every time a quantum event happens, one with multiple possible outcomes, the entire universe does not choose one path. Instead, it splits, fracturing into a near-infinite number of branches where every single possibility is realized. Theoretical physicist Sean Carroll champions this view, stating that the many worlds theory is not just a wild speculation, but a straightforward reading of the quantum equations. It is the universe refusing to make a choice. To understand this, we must first grasp quantum superposition, the bizarre principle that a particle like an electron can exist in multiple states or places at once until it is observed. In our everyday world, this seems impossible. A book is on a table or it is not, but in the quantum realm, the book is both on the table and on the floor and in your hands all at the same time. This leads directly to the famous, though unsettling, thought experiment of Schrödinger's cat. In one branch of reality, the cat in the box is alive and well. In another branch, in the very same moment, the cat has perished. Both are equally real. The mechanism that bridges this quantum weirdness with our solid, classical reality is called decoherence. Think of it as the process that separates these overlapping realities, allowing each new branch to develop independently, forever unaware of the others. There is no mysterious collapse of possibilities into a single outcome, only a continuous, silent branching of the cosmos. So what does this mean for you right now? How does the knowledge that a version of you is a celebrated artist while another is a quiet gardener change your feelings about the path you are on? Does it lessen the weight of regret, or does it make your specific journey feel more precious? This interpretation paints a cosmos of truly boundless possibilities, a multiverse where every story is told. And if the fabric of reality is this fluid, what does that say about the nature of the stage upon which it all plays out? That stage might be a vast, multidimensional loaf of cosmic bread. This brings us to our second theoretical journey, the Brane Multiverse from the depths of string theory. Here, our entire universe is not a solitary island in a void. It is a three-dimensional membrane, or brane for short, one slice in an unimaginably larger loaf. This cosmic loaf is called the bulk, a higher dimensional space that could contain countless other branes, each one a complete universe with its own unique set of physical laws. String theory proposes that the fundamental building blocks of reality are not point-like particles, but incredibly tiny, vibrating strings. For the mathematics of these strings to work, they require more than the three spatial dimensions we experience. They need extra dimensions curled up into sizes so infinitesimally small that we cannot detect them. Our brain traps all the forces and matter we know, like light and atoms, onto its three-dimensional surface. This is why we are so keenly aware of length, width, and depth, but completely blind to these other spatial dimensions. However, one force might be able to leak away. The renowned physicist Lisa Randall has explored how this brane world concept could solve a long-standing mystery, the hierarchy problem. She suggests that gravity, unlike the other forces, is exceptionally weak because it is not confined to our brane. It dilutes, spreading out into the vastness of the bulk. This is why the gravitational pull of an entire planet can be overcome by a small magnet. The magnet's force is trapped on our brane, concentrated and powerful, while gravity is seeping into other dimensions. This leads to a staggering possibility: another universe with different stars, different life, even different laws of physics, could be floating just a millimeter away from us. But that millimeter is not a distance we can travel in our 3 dimensions. It is a step into a higher direction we cannot point toward or move through. We are like paintings on a canvas, unable to perceive the other canvases hanging mere inches away in the gallery. Some theories, like the Ekpyrotic Universe model, take this even further. They propose that our Big Bang was not a singular eruption from nothingness, but the cataclysmic result of 2 branes colliding in the bulk. The immense energy of that collision, that cosmic slap, ignited the expansion of our entire reality. So the next time you feel confined by the world around you, remember that you may be living on a single sheet in a cosmic ream of paper, with entire other worlds hovering in a direction you cannot name. If our reality is just one membrane among many, what unseen structures could be weaving them all together into a single, coherent tapestry? Our 3-dimensional world, with all its depth and solidity, could be nothing more than an elaborate illusion. This is the heart of the 3rd theoretical journey, the holographic principle, a concept so profound it redefines the very nature of information and reality. The idea did not emerge from science fiction, but from the intense study of the most enigmatic objects in the cosmos, black holes. Physicists exploring black hole thermodynamics made a startling discovery. They found that the maximum amount of information that can be stored within any region of space is not proportional to its volume, as you might expect. Instead, it is proportional to the area of its boundary. Think of the universe not as a solid ball, but as a hollow sphere. The holographic principle suggests that everything happening inside that sphere, every star, every planet, every one of your thoughts, is actually encoded on its 2-dimensional inner surface, like a cosmic DVD. The theoretical physicist Leonard Susskind, one of the principle's co-discoverers, called it a radical new way of thinking about space, time, and matter. This means the rich, 3-dimensional reality we experience is a projection, a hologram emerging from a flat, 2-dimensional surface at the edge of the universe. This directly tackles one of the biggest puzzles in modern physics, the black hole information paradox. According to classical physics, when something falls into a black hole, all information about that object is lost forever, which violates a core tenet of quantum mechanics. The holographic principle provides an elegant solution. It posits that the information about everything that crosses the event horizon is not destroyed. It is perfectly preserved, encoded in 2 dimensions on the surface of the black hole itself. The most concrete realization of this mind-bending idea is a concept known as the anti-de Sitter/conformal field theory correspondence, often abbreviated as AD-SCFT. This is a powerful mathematical duality that provides a complete dictionary. It states that a gravitational theory operating in a hypothetical volume of space, which has specific properties, is perfectly equivalent to a quantum field theory without gravity operating on that volume's lower dimensional boundary. In simpler terms, it means the same physical system can be described in 2 completely different ways, one with gravity and extra dimensions, and one without. This is a monumental step toward a unified theory of quantum gravity, suggesting that gravity itself may not be a fundamental force, but an emergent phenomenon that arises from the complex quantum interactions happening on a distant, flat surface. So ask yourself this profound question. If the world you perceive as solid and real is ultimately a holographic projection, what does that imply about your own consciousness? Does your sense of free will retain its meaning if your choices are, in some fundamental sense, already written on a cosmic screen? This principle compresses our understanding of dimensions, suggesting that the universe's true workings are far simpler and more interconnected than they appear. It leads us to consider if the cosmos itself might be part of a grand, repeating cycle. The cosmos may not have a final ending, but an infinite series of new beginnings. Our fourth theoretical journey carries us into the realm of cyclical universes, a vision where the grand sweep of time forms an endless loop of birth, death, and rebirth. Proposed by the renowned physicist Roger Penrose, conformal cyclic cosmology reimagines the entire history of existence. It suggests that our universe is just one eon in an infinite chain, where the distant, heat-death future of one cosmos seamlessly becomes the hot, dense Big Bang of the next. Penrose offers a crucial clarification, stating that the universe can be cyclic without being identical in each cycle. This is not a simple repetition, like a film being rewound and played again. Each new eon inherits a kind of cosmic memory, a subtle imprint from its predecessor, allowing for infinite variation across the cycles. The mathematical magic that makes this possible is conformal geometry, a way of mapping shapes that allows you to stretch and shrink scales while preserving angles. In this framework, the universe at its end, stretched into a vast, cold emptiness of nearly massless particles, can be mathematically rescaled to look identical to the universe at its beginning, a hot, dense singularity. This rescaling acts as a cosmic reset button, but not for everything. One of the biggest hurdles for any cyclical model is the problem of entropy, the measure of disorder which always increases. If entropy carried over from one cycle to the next, each new universe would start with more chaos than the last, making the cycles impossible. Conformal cyclic cosmology provides an elegant solution. As the universe expands toward its end, all matter eventually decays into radiation, and black holes evaporate through Hawking radiation. In this final state of pure, uniform energy, the concept of entropy loses its meaning, effectively resetting to zero for the next Big Bang. The most tantalizing part of this theory is that it might leave behind observable evidence. Penrose and his colleagues believe they have found it in the cosmic microwave background, the faint afterglow of the Big Bang. They point to unusual circular patterns of warmer temperature, which they call Hawking points. These, they propose, are the final, imprinted echoes of supermassive black holes from the previous eon, their Hawking radiation leaving faint, concentric rings on the very fabric of our newborn universe. Another path to this cyclical rebirth involves a mysterious force known as phantom energy, a hypothetical form of dark energy so potent it could lead to a big rip. In this scenario, the expansion of the universe accelerates so violently that it tears apart galaxies, stars, planets, and eventually the very fabric of space-time itself. But from that ultimate dissolution, from that return to a uniform state, a new eon could be born, so we are left to reflect on a profound question. If the universe is truly cyclical, an endless dance of creation, does that imbue our existence with a sense of eternal recurrence? Does it make your life, with all its unique joys and sorrows, feel more meaningful, knowing it might be part of an infinite tapestry, or more fleeting, like a single note in a symphony that plays forever? This grand vision of time's loop naturally leads us to wonder about the very smallest scales of existence, where reality itself might be bubbling with potential. Beneath the grand cycles of cosmic rebirth lies a far more turbulent foundation, the very fabric of space-time, which we perceive as smooth and continuous, is actually a seething, chaotic froth at the smallest imaginable scale. This is the quantum foam, a concept born from the tumultuous marriage of quantum mechanics and Einstein's general relativity. The visionary physicist John Wheeler, who gave this phenomenon its name, described it perfectly, stating that spacetime is a foam-like structure at the Planck scale. This is not a gentle, soapy lather, but a violent, effervescent sea of energy where the rules of reality as we know them break down completely. To understand this foam, we must first grasp the Planck length. This is the smallest possible unit of measurement in the universe, a distance so incredibly tiny that it is to a single atom what an atom is to our entire solar system. At this minuscule scale, the smooth geometry of spacetime predicted by Einstein shatters. The uncertainty principle, a cornerstone of quantum mechanics, dictates that we cannot precisely know both the energy of a system and the time over which that energy exists. This leads to a profound consequence. Empty space is never truly empty. It is a frenetic dance of virtual particle pairs, particles and their antimatter counterparts, that spontaneously pop into and out of existence by borrowing energy from the vacuum before annihilating each other to repay the debt. This ceaseless activity is what creates the foam. The immense energy fluctuations warp the fabric of spacetime itself, generating a labyrinth of tiny, transient wormholes and even budding baby universes that appear and disappear in less than a blink of an eye. Imagine a spaceship engineered to be smaller than an atom trying to navigate this subatomic realm. Its journey would be anything but smooth. It would not sail through empty space. It would be violently tossed about, experiencing random, unpredictable jumps in position as it collided with the bubbling energy of the foam. Its trajectory would be a chaotic zigzag, a stark contrast to the straight lines we assume in our macroscopic world. This leads to a deeply unsettling question about the nature of our own experience. If the foundation of reality is this grainy and chaotic, how does that affect our fundamental notion of continuous motion and unbroken causality? The smooth arc of a thrown ball, the predictable orbit of a planet, even the steady flow of time from one second to the next, all of these may be illusions emerging from countless trillions of these random quantum jumps averaged together. Your sense of moving seamlessly through a stable world is a magnificent statistical miracle, a calm surface atop an infinitely deep and stormy ocean. This chaotic foam is the raw, untamed potential from which all more structured realities, including our own, may ultimately arise. From this frenzied sea of possibilities, how could more stable, orderly universes ever take shape? That same chaotic quantum foam may have been the seed for a process of cosmic inflation so powerful and enduring that it gave birth to our entire reality. The sixth theoretical journey takes us to the very beginning, to a fraction of a second after our universe's birth, when it underwent a staggering growth spurt known as inflation. Proposed by physicist Alan Guth, this theory solves several major puzzles about our cosmos, but it also leads to a breathtaking and perhaps inevitable conclusion: a multiverse. The core idea is that a peculiar energy field, known as the inflaton field, possessed a tremendous amount of potential energy. This energy caused the fabric of spacetime to expand at an exponential rate, far faster than the speed of light, smoothing out the universe and creating the vast, flat expanse we observe today. But the crucial detail is that this process did not stop everywhere at once. Think of a pot of boiling water. Bubbles form at different times and places. In the theory of eternal inflation, our universe is like that pot. Regions where the inflation field's energy drops stop inflating and become stable bubbles like our own observable universe. But the space between these bubbles continues to inflate at an incredible rate, forever pushing the newborn universes apart and creating an endless, growing mosaic of cosmic domains. As physicist Andre Linde, a key architect of this idea, stated, eternal inflation produces an infinite number of universes. This happens through a quantum process called false vacuum decay. Imagine the inflattened field is like a ball resting in a small dip on the top of a vast, flat hill. This is a false vacuum, a state of high energy that is temporarily stable but not truly the lowest energy state. Through a quantum fluctuation, the ball can tunnel through the energy barrier and roll down into the true valley below. When this happens in a tiny patch of space, that patch stops inflating and forms a bubble universe. But because the surrounding space is still inflating exponentially, it creates an endless cycle. New bubbles are constantly nucleating within the ever-expanding inflating background, a process without beginning or end. This connects deeply with string theory, which suggests there is not one unique vacuum state, but a colossal number of possibilities, perhaps 10 to the power of 500. This is the landscape of string theory vacua. Each of these distinct low-energy states corresponds to a different set of physical laws and constants. In the eternal inflationary multiverse, each bubble universe nucleates into a random point in this landscape. This means that the fundamental forces in one bubble might be stronger, in another weaker. The mass of an electron or the strength of gravity could be completely different. Our observable universe is just one single bubble where, by pure chance, the constants of physics allow for atoms, stars, planets, and life to form. This leads to a dizzying question that pushes the limits of our imagination. If the inflationary multiverse is truly infinite, then every universe that is physically possible must exist somewhere. Does this mean there is a bubble where you are a celebrated monarch, another where dinosaurs never went extinct, and another made entirely of crystal? The sheer scope of this idea is both exhilarating and humbling, suggesting that our entire cosmic history is just one page in an infinite book of possibilities. As we contemplate this endless expanse of worlds, we are drawn to a single, profound inquiry. Where does life, with its fragile and specific requirements, fit into this grand and chaotic cosmic tapestry? Our existence rests upon a knife edge of cosmic perfection. The seventh theoretical journey confronts the most baffling coincidence in all of science, the unsettling fine-tuning of the universe for life. If the strength of gravity were even slightly stronger, the universe would have collapsed back on itself in a fiery crunch moments after the Big Bang. If it were slightly weaker, galaxies and stars could never have coalesced from the primordial gas. This perfect balance is not an isolated case. The cosmological constant, which governs the energy of empty space and the acceleration of the universe's expansion, is fine-tuned to an astonishing precision of 1 part in 10 to the power of 120. A value any larger would have torn the cosmos apart before the first stars could form. Any smaller and gravity would have pulled everything back together. This incredible precision extends to the nuclear forces that govern the hearts of atoms. The strong nuclear force that binds protons and neutrons together is set just right. If it were a few % weaker, simple hydrogen would be the only element in existence. If it were slightly stronger, all the hydrogen would have been burned into heavier elements early on, leaving no fuel for stars like our Sun. The most beautiful example of this fine-tuning is found in the very heart of stars, in a process known as the triple alpha process. This is the stellar forge that creates the carbon essential for all known life. For this to happen, a precise and highly unlikely resonance must exist between the energy states of beryllium, helium, and carbon. The physicist Fred Hoyle famously predicted this resonance must exist based on the logical necessity of our own carbon-based existence, and experiments later proved him right. It was as if the laws of physics themselves were anticipating life. This overwhelming evidence for fine-tuning leads us directly to the anthropic principle, an idea articulated by physicist Brandon Carter. He stated that our location in the universe is necessarily privileged to the extent of being compatible with our existence. The principle comes in two forms. The weak anthropic principle simply observes that we must find ourselves in a universe capable of supporting life, because we are here to observe it. The strong anthropic principle takes a more profound stance, suggesting that the universe must have parameters that allow life to develop at some point in its history. So how do we explain this incredible luck? The multiverse provides a powerful and natural answer. In an infinite or near-infinite multiverse, born from eternal inflation or the string theory landscape, every possible combination of physical constants and laws will be realized in some pocket universe. We do not live in a special universe designed just for us. We simply live in one of the exceedingly rare bubbles where the constants randomly fell into the narrow window that permits atoms, planets, and ultimately, observers to arise. In the vast majority of universes, the conditions are sterile and lifeless, with no one to wonder why. Does this realization make you feel insignificant, a mere statistical fluke in a cosmic lottery? Or does it make your existence feel all the more precious, a rare and beautiful spark of consciousness in an otherwise silent eternity? The anthropic principle inextricably links the fact of our life to the architecture of the cosmos, forcing us to consider an even more radical possibility. If the universe seems engineered for observation, could that observation itself be part of a programmed reality? The universe may not be a grand, physical cosmos, but an intricate digital creation running on a computer of almost unimaginable power. This is the eighth theoretical journey, the simulation hypothesis, a concept that reframes alternate dimensions as nothing more than distinct software instances operating within a vast computational system. Philosopher Nick Bostrom formalized this startling idea, presenting a compelling trilemma. He argues that at least one of three propositions must be true. Either civilizations inevitably go extinct before reaching a post-human stage of technological capability, or any advanced civilization has no interest in running ancestral simulations, or we are almost certainly living in a simulation. If even a tiny fraction of advanced civilizations choose to create realistic simulations of their history, the number of simulated minds would vastly outnumber the biological ones. From a statistical standpoint, it is far more likely that we are among the simulated beings. This logic has resonated with figures like Elon Musk, who has publicly stated his belief that the odds we are in base reality, the original physical world, are 1 in billions. The core of this argument rests on a principle known as substrate independence. This is the idea that consciousness is not inherently tied to biological wetware like our brains. It is a pattern of information processing. If that pattern can be supported by silicon chips or some other advanced computing substrate, then the conscious experience would be just as real and valid. The only limitation is processing power. To simulate an entire universe down to the quantum level would require computational resources beyond our current comprehension. Yet, from our own rapid technological progress, we can extrapolate the potential of a civilization thousands or millions of years more advanced. Our own rudimentary quantum computers, which leverage the bizarre principles of superposition to perform calculations, hint at a future platform where simulating a universe might not just be possible, but efficient. This digital lens even offers a new interpretation for some of the deepest puzzles in physics. The finite resolution of spacetime at the Planck scale, the tiniest possible unit of distance, acts exactly like the pixels on a high-definition screen. There is a fundamental limit to how small you can zoom in, a built-in pixelation of reality itself. Could the strange results of the double-slit experiment, where particles seem to behave as waves until observed, be a rendering optimization? The simulation only calculates the precise path of a particle when a conscious observer is looking, saving processing power the rest of the time. Even déjà vu or seemingly random cosmic rays could be explained as minor software glitches or background processes in the cosmic computer. This leads to a deeply ethical and unsettling question. If we are living in a simulated reality, what responsibilities do our potential programmers hold? Are we merely entertainment for a post-human civilization, a historical research project, or perhaps a training simulation for their own development? The morality of creating sentient beings who experience pain, joy, and loss within a constructed world is a philosophical minefield. Are they obligated to intervene in our suffering, or would that violate the integrity of their experiment? Your entire life, with all its love and heartache, could be part of a grand digital narrative. This hypothesis forces a profound shift in perspective, reducing the solidity of the world to an elegant mathematical structure. It suggests that the true nature of reality is not matter or energy, but information. If our universe is fundamentally mathematical, then what other breathtaking structures could be waiting to be discovered in the abstract realm of pure logic? The ultimate nature of reality may not be physical at all, but a perfect, immutable mathematical structure. This is the ninth theoretical journey, the mathematical universe hypothesis, championed by physicist Max Tegmark, who makes the bold claim that our external physical reality is a mathematical structure. He argues that we do not just use mathematics to describe the universe. We are living inside a giant mathematical object. In this view, every self-consistent mathematical structure doesn't just describe a possible universe, it is a universe. Alternate dimensions and alternate realities are simply different mathematical sets, each with its own unique axioms and properties. Tegmark organizes this dizzying concept into a four-level multiverse. Level 1 is the simplest, an infinite space where every possible configuration of matter is repeated over vast distances. If you travel far enough, you will find an identical copy of Earth and of you. Level 2 emerges from the eternal inflation we discussed, a vast collection of bubble universes with different physical constants. Level 3 is the many worlds of quantum mechanics, where every quantum possibility branches into a new reality. But the ultimate, Level 4 multiverse contains every single mathematical structure that can exist. A universe where the rules are based on simple arithmetic is just as real as one governed by the complex equations of string theory. This leads us directly to a profound puzzle in the foundation of mathematics itself, Gödel's incompleteness theorems. In the 1930s, logician Kurt Gödel proved that within any sufficiently complex mathematical system, there will always be true statements that cannot be proven from within the system. The system can never be both complete and consistent. If our universe is a mathematical structure, does Gödel's work imply that there are truths about our reality that are fundamentally unprovable, forever beyond the reach of our scientific inquiry? To make this abstract idea tangible, consider the geometry of space. Our universe appears to be governed by non-Euclidean geometry, where parallel lines can eventually meet or diverge. But what about a universe built on classical Euclidean geometry, where parallel lines remain forever parallel? According to the mathematical universe hypothesis, that universe exists. It is a real, physical place with its own stars, planets, and perhaps even life forms adapted to that rigid, flat spatial fabric. They would experience a reality as solid and real as our own, yet their foundational rules would be different. This forces a deep philosophical question. If mathematics is the ultimate reality, are we discovering these dimensions and laws, uncovering a pre-existing cosmic blueprint? Or are we merely inventing them, constructing the rules as we go along? The hypothesis strongly suggests we are explorers, not creators, mapping out the contours of a reality that was always there. And what of our own consciousness in this vast mathematical library? If our minds are simply complex computations, then they too are mathematical patterns. Your sense of self, your memories, your hopes and fears, could be a specific, intricate equation being solved within the grand structure of a mathematical cosmos. You are not just using math, you are math. This abstract journey compresses all of existence into an elegant, logical framework, suggesting that the multiverse is not just a physical place, but an infinite encyclopedia of pure reason. From this ethereal realm of perfect forms, we are pulled toward a more structured and tangible kind of higher dimensional space, one that might finally explain the very forces that hold our world together. A fourth spatial dimension would fundamentally rewrite the laws of physics as we know them. This 10th theoretical journey takes us beyond time into a realm of pure geometry, an additional direction that is utterly perpendicular to our familiar length, width, and depth. To even begin to grasp such a concept, we must shrink our own perspective, stepping into the two-dimensional world of Edwin A. Abbott's classic tale, Flatland. In this fictional realm, beings are simple geometric shapes, living their entire lives on a flat plane, completely unaware of the vast universe above and below them. They can move forward, backward, left, and right, but the idea of up or down is as incomprehensible to them as a fourth spatial direction is to us. If a three-dimensional being, like a sphere, were to descend into Flatland, the inhabitants would not perceive the sphere itself. They would only witness a mysterious series of events. First, a single point would appear in their world. As the sphere passed through their plane, that point would grow into a small circle, which would expand to a maximum diameter before shrinking back down to a point and vanishing. To a Flatlander, this would be a miracle, an object materializing from nothing, changing size, and then disappearing without a trace. This is precisely how physicist Kip Thorne clarifies the concept, stating that the fourth dimension is not time, it is an additional spatial dimension. We are the Flatlanders of a three-dimensional world, and a four-dimensional object passing through our space would create an equally baffling spectacle. Imagine a hypercube, the four-dimensional analog of a cube. As it moved through our three-dimensional slice of reality, we would not see the entire object at once. We would witness its three-dimensional cross-section, which would appear as a cube that mysteriously grows, changes shape, and perhaps even rotates in impossible ways before fading from view. This is not magic, it is simply geometry unfolding in a higher dimension. The mathematics of such objects is robust, describing structures with properties that seem like pure fantasy. This idea moves from abstract geometry to testable physics with theories that suggest gravity, the weakest of the fundamental forces, might be weak because it is not confined to our three-dimensional brain. It could be leaking away, dissipating into these extra spatial dimensions. This is why the gravitational pull of an entire planet can be overcome by a small magnet. The magnet's electromagnetic force is trapped on our three-dimensional membrane, concentrated and powerful, while gravity is spreading out into unseen higher directions. Scientists are actively searching for evidence of these extra dimensions. Powerful particle colliders like the Large Hadron Collider are one frontier. If extra dimensions exist, they could provide a pathway for energy to disappear from our universe during high-energy collisions. We would detect a mysterious missing energy, a signature that something had escaped our dimensional prison. Other experiments are searching for deviations in the inverse square law of gravity at incredibly small scales. If gravity is leaking into extra dimensions, its strength should fall off faster than expected at sub-millimeter distances. So far, no definitive signal has been found, but the hunt continues. If we could truly access and move through a fourth spatial dimension, the implications would be beyond revolutionary. Would it be a form of teleportation to a flatlander, a three-dimensional being lifting a square off the plane and placing it back down in a distant location would seem like instant travel. From our perspective, the square simply vanished and reappeared elsewhere. In the same way, a four-dimensional being could pluck you from your current location and place you anywhere in our three-dimensional world without traversing the space in between. As for time travel, the connection is more subtle. While a fourth spatial dimension is not time itself, the ability to move through higher spatial dimensions could potentially offer shortcuts through spacetime, creating closed paths that might allow for journeys to the past. This spatial expansion of our reality forces us to confront the very architecture of the cosmos. If gravity is so deeply connected to these hidden dimensions, what other profound secrets might they hold about the force that literally shapes our universe? Gravity and light may be two faces of a single, deeper reality. This 11th journey takes us back to a revolutionary idea from the early 20th century, a time when Einstein's general relativity was reshaping our understanding of the cosmos. In 1919, a little-known mathematician named Theodore Kaluza made a breathtaking proposal. He took Einstein's equations, which describe gravity as the curvature of four-dimensional spacetime, and simply rewrote them for a universe with 5 dimensions. The result was nothing short of magical. From the mathematics of this 5-dimensional world, Einstein's equations for gravity emerged naturally, but something else appeared alongside them, the familiar equations of James Clerk Maxwell for electromagnetism. In one elegant stroke, Kaluza had seemingly unified the two fundamental forces known at the time, suggesting they were not separate at all, but different aspects of a single, geometric truth in a higher dimensional space. The obvious problem was, where is this 5th dimension? We only experience 3 dimensions of space and 1 of time. Physicist Oscar Klein provided the crucial answer a few years later. He proposed that this extra spatial dimension is not large and expansive like the others. It is compactified, curled up into a fantastically tiny loop at every single point in space. To understand this, imagine looking at a long, thin garden hose from a great distance. It appears to be a simple one-dimensional line, but as you move closer, you discover its two-dimensional surface, a cylindrical shape that was always there, just hidden from your macroscopic view. According to Klein, our entire three-dimensional space is like that distant view of the hose. At every point, if we could zoom in to an inconceivably small scale, we would find these tiny, curled-up circles, a direction we cannot point to or move in because it is smaller than any particle we can measure. The size of this curled-up dimension is known as the compactification radius. Klein calculated this radius to be on the order of the Planck length, a distance so minuscule that it is a billion trillion times smaller than a single proton. This is precisely why we do not perceive this dimension directly. Our most powerful particle accelerators probe distances trillions of times larger than this, so the 5th dimension remains completely hidden from our experiments. However, its existence would have profound and potentially detectable consequences through what are known as Kaluza-Klein modes. Think of the compactified dimension as a tiny, vibrating loop. Just as a guitar string can vibrate at different frequencies to produce different notes, this tiny dimension can also vibrate in distinct patterns. Each of these vibrational modes would correspond to a new, massive particle from our three-dimensional perspective. If we could probe high enough energies, we would not see just one type of electron, but a whole tower of increasingly heavy copies, each one a different harmonic of the fundamental vibration of the compactified dimension. The lightest particle in each tower is the one we know and observe, while its heavier partners are just beyond our current energy reach. This elegant idea of hidden dimensions and their vibrational modes did not fade away. It became the direct precursor to modern string theory, which expands the concept from one curled-up dimension to 6 or 7, with the vibrations of fundamental strings through this complex geometric landscape, giving rise to all the particles and forces of nature. So we are left with a tantalizing question. If these extra dimensions are woven into the fabric of reality at every point, why does their subtle signature continue to elude our most determined searches? This elegant unification of forces through geometry points the way toward an even more ambitious and symmetrical framework for the cosmos. Supersymmetry proposes a breathtakingly elegant partnership at the heart of reality, a deep symmetry that connects the two fundamental classes of particles in the universe. On one side, you have the fermions, the building blocks of matter like quarks and electrons. On the other, you have the bosons, the force carriers like photons and gluons. Supersymmetry suggests that for every known fermion, there is a massive, undiscovered bosonic partner, and for every boson, a fermionic twin. This is why physicist Michio Kaku can state that supersymmetry doubles the number of particles in the universe. The electron, a fermion, would be paired with a boson called the selectron. The quark, another fermion, would partner with the squark. Conversely, the photon, a boson, would be matched with a fermion known as the photino. This elegant doubling is not just for aesthetic appeal. It provides a powerful and natural solution to one of physics' most nagging issues, the hierarchy problem. This problem asks why the force of gravity is so unimaginably weaker than the other fundamental forces. The mathematics of the Standard Model suggests that the mass of the Higgs boson should be driven up to an enormous scale by quantum fluctuations, yet it remains relatively light. Supersymmetry solves this because the contributions from Standard Model particles and their superpartners cancel each other out with perfect precision. For every particle that pushes the Higgs mass upward, its superpartner pulls it down, creating a delicate balance that keeps the mass, and by extension our universe, stable. This symmetry is a cornerstone of string theory, which is why it is often called superstring theory. The theory requires these supersymmetric partners for its mathematical consistency in 10 dimensions. The extra dimensions in superstring theory are not optional. They are a necessity, compactified into intricate shapes known as Calabi-Yau manifolds. The specific geometry of these 6 extra dimensions determines the vibrational patterns of the strings, which in turn dictates the properties of the particles and forces we observe in our 4-dimensional world. This leads to the staggering landscape of string theory vacua, a vast collection of possible solutions, each corresponding to a universe with different physical laws. Within this symmetric framework, a particularly compelling candidate for dark matter emerges. In most supersymmetric models, a quantum property called R-parity is conserved. This means that the lightest supersymmetric particle, often the neutralino, a mix of the photino and other partners, would be completely stable. It would not decay into anything else. Created in the hot early universe, these particles would still be drifting through space today, invisible and barely interacting, yet exerting a powerful gravitational pull. They could form the very dark matter halos that hold galaxies together. The search for these superpartners has been a primary goal of the world's largest particle colliders, like the Large Hadron Collider. So far, the detectors have remained silent, finding no direct evidence for selectrons or squarks. This forces physicists to consider that supersymmetry, if it is a law of nature, might be broken. The superpartners could be far heavier than initially hoped, pushing their discovery to the next generation of colliders. This introduces a profound question. If supersymmetry is real, what new particles await discovery in the high-energy frontier? Finding them would not just add to a list, it would open a door to a more unified and symmetric cosmos, revealing a hidden layer of reality where matter and force are two expressions of a single, deeper truth. This elegant framework, with its partners and hidden dimensions, beautifully sets the stage for a new vision of our cosmic home, one where our entire universe is a dynamic membrane floating in a higher dimensional bulk. Our universe might be confined to a membrane, a three-dimensional island adrift in a warped, five-dimensional sea. This is the 13th theoretical journey, the Randall-Sundrum Model, a brilliant framework developed by physicists Lisa Randall and Randall-Sundrum. They envisioned our cosmos as a three-brane existing within a five-dimensional bulk, but this is not the flat, featureless space of earlier ideas. This bulk is an anti-de Sitter space, a geometry with a constant negative curvature that warps spacetime itself in a profound way. The model's most stunning feature is that gravity is not a universal force spread evenly throughout this five-dimensional realm. Instead, it is sharply localized, concentrated on a separate brane some distance away from our own. This single geometric arrangement provides an elegant and powerful solution to the hierarchy problem, the puzzle of why gravity is so incredibly weak compared to the other fundamental forces. The immense warp of the spacetime between the branes creates an exponential suppression of gravity's influence on our world, explaining its feebleness without requiring any extra dimensions to be microscopically small. This framework comes in two compelling variants known as RS1 and RS2. The RS1 model presents a finite, warped fifth dimension bounded by two branes. Our universe resides on the weak brane, where gravity is diluted. The other is the Planck brane, where gravity is naturally as strong as the other forces. The warping is described by a mathematical term called the warp factor, an exponential function that scales all energy masses as one moves across the fifth dimension. A fundamental particle with a mass of, say, the Planck mass on the gravity brane would appear to have a mass of only 1,000 times the proton's mass on our brane. This immense scaling down is how the model naturally generates the vast difference between the strength of gravity and the other forces. The RS2 model simplifies this picture, removing the second brane and sending it to infinity. In this scenario, our brane is isolated in an infinite, warped fifth dimension. While this might seem to render gravity impossibly weak, the intense warping of the anti-de Sitter space itself acts to localize gravity, creating a force that behaves exactly like our familiar, weak gravity on the brane while falling away sharply in the bulk. This warped geometry gives rise to new, massive particles that could be detected. Just as in the Kaluza-Klein model, the gravitational field in the fifth dimension can vibrate. These vibrations manifest in our four-dimensional world as a series of massive partner particles to the graviton, the hypothetical quantum of gravity. These are the Kaluza-Klein gravitons. Unlike the massless standard graviton, these partners are heavy, and they would interact very weakly with the matter on our brain. This makes them a prime target for discovery at particle colliders like the Large Hadron Collider. The experimental signature would be truly spectacular and bizarre. If these Kaluza-Klein gravitons were produced in a high-energy collision, they would immediately vanish from our brain, escaping into the bulk. From our perspective, the collision would result in a dramatic and unexplained missing energy, a clear sign that something had literally left our dimensional plane. The intuitive way to picture why gravity is so weak on our brain is to think of it as leaking or diluting into the vastness of the bulk. Imagine our three-dimensional world is a vast, flat sheet of paper. Gravity is not confined to this sheet. It is like a subtle energy that soaks through the paper and spreads out into the surrounding three-dimensional room. The force becomes diluted, its strength fading as it occupies a much larger volume. This stands in stark contrast to forces like electromagnetism, which are like ink trapped entirely on the surface of the paper, remaining concentrated and powerful. This leads to a fascinating cosmic question. If gravity is localized on a separate brane in the RS1 model, could that other brane host an entire universe where gravity is as potent as electromagnetism is for us? In such a reality, a civilization might build structures with a mere whisper of material, their bodies adapted to a crushing gravitational force that is the norm. Their entire experience of physics would be fundamentally, unimaginably different from our own. This brane-based perspective naturally flows into the exploration of dark dimensions, a related concept where a single, large extra dimension could house the mysterious particles that make up dark matter. The idea that our visible universe is just one membrane in a richer, higher-dimensional cosmos continues to challenge and inspire, suggesting that the deepest secrets of reality may be hiding not in the far reaches of space, but in the unseen directions that lie all around us. Dark energy itself could be a signal from a hidden direction in space. The 14th theoretical journey introduces the dark dimension scenario, a compelling proposal where the mysterious force accelerating the universe's expansion is tied directly to a single, large extra dimension. This is not the infinitesimally small, curled-up dimension of Kaluza and Klein, but one potentially as large as a micrometer, a scale just beyond our current ability to measure but enormous by the standards of particle physics. This idea emerges from the swampland program in string theory, an ambitious effort to distinguish which effective field theories can be consistently completed into a full theory of quantum gravity in the string theory landscape, and which are doomed to the swampland, forever incompatible. A key conjecture from this program suggests that in a consistent theory of quantum gravity, the vacuum energy, which manifests as dark energy, cannot be arbitrarily small and static. It must be able to decay or be mobile. The dark dimension scenario provides a stunningly elegant mechanism for this. It proposes that our four-dimensional universe is coupled to this large, dark dimension, and the incredibly small but positive value of our cosmological constant is not a fixed parameter. It is a dynamical field, a modulus that is slowly rolling toward a lower energy state. This process of moduli stabilization, where these fields find their stable values, is crucial. As this field evolves, it drives the accelerated expansion of our universe while also causing the dark dimension itself to contract over cosmological timescales. This creates a direct, tangible link between the vast, accelerating cosmos and the geometry of a hidden dimension. For particle physics, the implications are profound. The existence of such a large extra dimension would give rise to a vast spectrum of new, very light particles. These would be Kaluza-Klein partners of the graviton, but with exceptionally small masses due to the large size of the dimension. This entire tower of ultra-light states is a candidate for dark matter, a continuous veil of invisible particles that fills the cosmos and sculpts the growth of galaxies. The most exciting aspect is that this theory is testable. It predicts specific, detectable deviations from Newton's law of universal gravitation at distances around a micrometer. Exquisitely sensitive tabletop experiments are already searching for these deviations, using tiny, suspended mirrors to measure the gravitational force between objects at these microscopic scales. Finding a break from the inverse square law at such a small distance would be a monumental discovery, our first direct evidence of an extra dimension and a revolutionary explanation for dark energy. Does this connection simplify the grand mysteries of cosmology? It reframes them, weaving dark energy, dark matter, and the fabric of space-time itself into a single, geometric narrative. This interplay between vacuum energy and cosmic evolution naturally guides us toward a powerful, and perhaps even more radical, idea for how the universe self-corrects its own laws. Black holes might be the cosmic wombs for new universes. This 15th theoretical journey, Cosmological Natural Selection, envisions a cosmos where the laws of physics themselves are not fixed, but are shaped by a grand Darwinian evolutionary process. Proposed by physicist Lee Smolin, this radical idea applies the principles of natural selection to the cosmos itself. Smolin makes the bold claim that the laws of physics evolve by natural selection. In this framework, a universe that is particularly adept at producing black holes is, in essence, a reproductively successful parent. The theory begins with the life cycle of a black hole. When a massive star collapses, it forms a singularity, a point of infinite density where our known laws of physics break down. Cosmological natural selection proposes that this singularity does not mark an end, but a new beginning. It births a new universe in a separate branch of space-time, a daughter universe with its own Big Bang. This new cosmos inherits its physical constants from its parent, but with a crucial twist. The process is not perfect. Just as DNA can mutate when passed to offspring, the fundamental parameters like the strength of gravity or the mass of an electron might be slightly tweaked in this cosmic reproduction. This introduces variation, the raw material for evolution. Over countless generations, a fitness landscape for universes emerges, a universe where the constants are perfectly tuned for prolific black hole production is highly fit. It will spawn a vast number of offspring universes which will inherit those successful traits. A universe where the constants do not permit black holes to form is an evolutionary dead end, a sterile branch in the cosmic tree of life. An illustrative scenario makes this vivid. Imagine a universe where the cosmological constant is slightly smaller than our own. This would allow more matter to clump together earlier, forming more massive stars that live fast and die young in spectacular supernova, leaving behind a greater number of black holes. This universe would outbreed its neighbors, and over cosmic time, universes like it would come to dominate the multiverse. This provides a powerful, non-anthropic explanation for the fine-tuning we observe. Our universe is not special because it allows for life. It is special because its constants happen to fall within the narrow window that also, coincidentally, allows for the abundant production of black holes. Life in this view is a fortunate byproduct of a cosmos optimized for stellar collapse. This theory even offers testable predictions. If our universe is finely tuned for maximum black hole production, then the distribution of masses for neutron stars, the densest objects just shy of becoming black holes, should reflect this. We should find a statistical pile-up of neutron stars near the maximum mass possible before they must collapse into a black hole. Current astrophysical observations are scrutinizing this very prediction. So we are left to ponder a profound question. If universes truly evolve, are we living inside a particularly fit specimen, a cosmic champion in the relentless competition to create more black holes? This evolutionary perspective reframes eternal inflation not as a random process, but as a cosmic ecosystem, teeming with life cycles and inherited traits. From this cycle of cosmic birth and death, we are drawn to a different kind of emergence, one where the very flow of time might be a story we tell ourselves. The violent birth of our cosmos might have been a collision in the dark. The 16th theoretical journey, the Ekpyrotic Universe model, reimagines the Big Bang not as an eruption from a single point of infinite density, but as the cataclysmic result of two cosmic membranes smashing together in a higher dimensional space. Developed by physicists like Paul Steinhardt, this framework presents a compelling alternative to inflation, one that entirely sidesteps the need for an initial singularity where all known physics breaks down. In this cyclic vision, our universe is a three-dimensional brane, and it exists alongside at least one other parallel brane, both of them floating in a vast, higher dimensional bulk. These branes are not static. They are dynamic, oscillating sheets drawn together and pushed apart by mysterious forces over inconceivably long eons. The event we call the Big Bang was simply the moment these two titanic membranes collided. The immense kinetic energy of that impact was instantly converted into the hot, dense soup of particles and radiation that would eventually expand to become our entire observable universe. This process avoids the perplexing singularity, offering a more physically plausible starting point. But this elegant picture faces its own profound challenge, the entropy problem. The second law of thermodynamics states that entropy, or disorder, always increases. If the universe has undergone an infinite number of these cycles, why is the entropy not already at a maximum, creating a featureless, high-entropy sea incapable of forming galaxies or stars? The Ekpyrotic model provides a clever resolution. In this cyclic scheme, the universe expands by a colossal factor in each cycle, but it never grows so large and dilute that it reaches a maximum entropy state. The entropy from previous cycles is effectively diluted by the immense new volume created in the next expansion, allowing the cosmos to reset its thermodynamic clock with each new collision. A crucial player in this endless dance is dark energy. In the Ekpyrotic scenario, dark energy is not a constant force leading to an eternal, lonely expansion. Instead, it acts as the engine of the cycle. After a brane collision ignites a new universe, dark energy dominates, driving a period of accelerated expansion that stretches and smooths the cosmos. But this phase eventually ends, allowing the branes to be drawn together once more by a mysterious attractive force, setting the stage for the next collision and the next Big Bang. This leads to a testable prediction that distinguishes it from standard inflation. The violent, shearing motion of two branes scraping past each other would generate a unique background of gravitational waves, ripples in spacetime itself. However, the spectrum of these waves would be very different from those predicted by inflationary models. Future observatories, like space-based gravitational wave detectors, could potentially find this signature, offering our first direct evidence of a cosmic event that occurred before our own universe began. This model presents us with a dizzying, infinite regress. If our Big Bang was a brane collision, what set the stage for that collision? It must have been the expansion phase of a previous cycle, which itself began with a collision, and so on, backward and forward in time forever. Are we living in just one note of an endless cosmic symphony, a single breath in an eternal cycle of creation? This vision of a cyclical cosmos without beginning or end forces us to confront the very nature of time itself. Is time a fundamental arrow, or is it merely a measure of change within an eternal, repeating structure? Your entire life, from your first breath to your last, might already be written into the fabric of the cosmos. The 17th theoretical journey presents the block universe, a vision where past, present, and future do not flow in a sequence but coexist eternally in a single, four-dimensional structure. This is the philosophy of eternalism, and it finds its strongest support in Einstein's own theory of relativity. Time, in this view, is not a river carrying us forward. It is simply another dimension, much like length, width, and depth, a coordinate in a grand cosmic map where every event has its permanent place. Philosopher J.M.E. McTaggart argued for the unreality of time by distinguishing between two series. The A series sees events as constantly changing from future to present to past, a flowing now we all feel. The B series is a static ordering of events, where everything is just earlier than or later than something else, with no special present moment. Eternalism and the block universe embrace the B series, suggesting the flowing now is a powerful, persistent illusion of consciousness. The foundation for this timeless reality comes directly from special relativity, through the relativity of simultaneity. Two events that appear to happen at the exact same moment for one observer can occur at clearly different times for another observer moving at a high speed. There is no universal, privileged now that sweeps across the cosmos. Your present moment is not the same as the present moment for an astronaut on a fast-moving spacecraft near a distant star. This shatters the common-sense idea of a single, progressing present. In the block, every moment is equally real. Your 5th birthday party is not gone. It is still there in the past section of the block. Your retirement party is already there in the future section. You are simply not conscious of it yet. We can visualize this using the concept of world lines. Imagine a long, loose strand of spaghetti stretched through a 4-dimensional loaf of bread. That strand is your world line, your complete path through spacetime. The entire loaf is the block universe. At this very moment, you are not a 3-dimensional object at a single point in time. You are the entire 4-dimensional worm of your existence from birth to death. We perceive our lives moment by moment because our consciousness, for reasons we do not understand, seems to move along this world line, illuminating one cross-section at a time. This is akin to a time traveler. We think nothing of moving through the 3 dimensions of space. We can go left or right, forward or backward. A being that could move freely along the time dimension could visit your childhood or your old age as easily as you can walk from your kitchen to your living room. To such a being, your life would be a static, completed sculpture. This framework forces a deep confrontation with free will and causality. If the future is already out there, set in the stone of space-time, are our choices truly free? Or is our agonizing over decisions merely the process of discovering a path that was always destined? In the block universe, your feeling of making a choice is real, but the outcome of that choice may be as fixed as the date on a historical monument. This does not necessarily make life meaningless. It might instead mean that your entire story, with all its struggles and triumphs, possesses a kind of eternal, unchangeable beauty. This timeless perspective finds a strange harmony with the quantum many-worlds interpretation. If every quantum possibility branches into a new reality, then the block universe might not be a single, monolithic structure. It could be a vast, growing block, or a tapestry of countless parallel blocks, each one a complete timeline where every possible version of history plays out to its conclusion. Are we navigating a single, predetermined path, or are we selecting, moment by moment, which of an infinite number of already existing blocks we will become aware of. The universe does not split with a bang, but with a whisper, through the quiet, relentless interaction of every particle with its surroundings. This 18th journey refines the branching multiverse, grounding it in the tangible physics of quantum decoherence. Where the original many worlds interpretation presented a stark picture of instantaneous splitting, decoherence theory explains the how and the why, revealing the gradual process that makes parallel worlds classical and real. As physicist Wojciech clarifies, decoherence is what makes the classical world emerge from the quantum. It is the mechanism that transforms fuzzy quantum superpositions into the definite realities we perceive. The core of this process is environmental interaction. A quantum system, like a lone electron, can happily exist in a superposition of multiple states. But the moment it is exposed to its environment, even a single photon of light or a molecule of air, information about its state begins to leak out. This constant monitoring by the environment forces the system to choose, not once and for all, but in a way that makes other possibilities effectively invisible to any local observer. This selection process picks out what are known as pointer states. These are the specific, stable states of a system that are robust against environmental disruption. Think of a spinning top. It can wobble in many unstable ways, but its pointer state is stable, upright rotation. In the same way, for Schrödinger's famous cat, the pointer states are not alive and dead, a fragile quantum superposition. The environment, in the form of air molecules, radiation, and even the faintest background warmth, instantly interacts with the cat. This interaction rapidly decoheres the system, selecting the classical pointer states, a cat that is definitively alive in one branch or definitively dead in another. The transition from quantum to classical is not a fundamental boundary. It is a practical one governed by the speed and scale of decoherence. A single electron can maintain its quantum coherence for a relatively long time, isolated in a vacuum. But a complex object like a cat, composed of trillions upon trillions of particles, decoheres almost instantaneously because it is constantly buffeted by its environment. There is no single moment of splitting, only a swift and irreversible loss of quantum connection between the emerging branches. This leads to a staggering, almost palpable question. If decoherence is continuously creating robust, classical worlds from quantum possibilities, how many new branches are splitting off around you at this very second? Every quantum event, from the decay of a radioactive atom in a distant star to the unpredictable path of a photon reflecting off your screen, is a potential point of divergence. Your reality is not a single thread, but the trunk of an endlessly forking tree, with new branches sprouting into concrete existence faster than thought. This elegant process provides the physical underpinning for the reality of parallel worlds, suggesting that the multiverse is not a philosophical abstraction but a dynamic, emergent structure. And if the world around you is born from this process of environmental interaction, where does your own conscious observation, your unique vantage point, fit into this rapidly dividing cosmos? Your own conscious awareness might be the final arbiter of reality itself. The 19th theoretical journey places the human mind at the very center of the quantum mystery, proposing that consciousness is not a passive bystander but the active force that collapses the wave function. This is the von Neumann-Wigner interpretation, a perspective developed by the brilliant mathematician John von Neumann and later championed by physicist Eugene Wigner. They argued that the chain of quantum measurement cannot be completed by any physical device. A Geiger counter or a photographic plate simply becomes part of the larger quantum system, entering a superposition itself. Only when the information from that device registers in the mind of a conscious observer does the superposition finally collapse into a single, definite state. Wigner himself pondered this deeply, suggesting that it was not possible to formulate the laws of quantum mechanics in a fully consistent way without reference to consciousness. This interpretation confronts the hard problem of consciousness head-on. This is the profound mystery of why and how physical processes in the brain give rise to subjective experience, the inner movie of sights, sounds, and feelings that is your life. Materialist critics offer a powerful counterargument. They assert that consciousness is an emergent property of complex neural computation, a phenomenon that arises from the brain's physical structure. From this viewpoint, there is nothing special about a human observer. A sophisticated computer or even a simple detector could cause decoherence and collapse the wave function just as effectively, with no inner experience required. The debate often centers on a thought experiment known as Wigner's friend. Imagine a physicist, Wigner, outside a sealed laboratory. Inside, his friend conducts a quantum experiment, say, measuring the spin of an electron. According to standard quantum mechanics, the friend and the entire lab enter a superposition from Wigner's perspective until he opens the door and asks for the result. But what was the reality for the friend inside? Did she experience a definite outcome the moment she looked, or was her consciousness also in a blurry superposition until Wigner's observation collapsed her world? This leads to the staggering possibility of personal dimensions. If your consciousness truly determines your reality, then your subjective experience could be a unique, self-contained dimension. Through deep meditative states where the normal chatter of the mind is quieted, could you learn to influence this quantum selection process? Might advanced practitioners of mindfulness be subtly steering their awareness toward branches of reality that are slightly more peaceful, more focused, or even physically different from the consensus world? The idea that your mind could shape the cosmos is both empowering and isolating. It suggests that your reality is, in a very literal sense, your own creation. This profound link between observer and the observed naturally guides us to consider a universe where information is the most fundamental currency of all. The very substance of reality might boil down to pure, abstract information. This 20th theoretical journey introduces the it from bit philosophy, a profound vision from the great physicist John Archibald Wheeler. He proposed that every particle, every field of force, even space-time itself, is not fundamentally physical. Instead, it all emerges from immaterial bits of information. In Wheeler's own words, it from bit suggests that every item of the physical world has at bottom an immaterial source and explanation, that what we call reality arises in the last analysis from the posing of yes-no questions and the registering of equipment-evoked responses. Imagine the universe posing an endless series of binary questions. Is a particle here or is it there? Is it spin up or is it down? The answer to each question, a simple 1 or 0, a single bit, defines the state of that particle. Countless trillions of these yes-no answers, asked and registered at every moment, weave together the tapestry of the world we perceive. This philosophy provides a beautiful, deeper foundation for the holographic principle we explored earlier. The two-dimensional surface encoding our three-dimensional reality is not just a screen, it is a cosmic hard drive. The information density of that surface, with its finite number of Planck-sized pixels, represents the total memory capacity of our universe. Everything within the volume is a projection, a computation derived from the data stored on that boundary. This connects seamlessly with quantum information theory, which treats quantum states not as physical attributes but as units of information. The strange phenomenon of quantum entanglement, where particles remain connected across vast distances, can be seen as a perfect correlation in their shared information. When you measure one particle, you instantly update the information state of its partner, no matter how far apart they are. This is not spooky action at a distance, but a fundamental reflection of a deeply informational cosmos. We can take the analogy of a cosmic computer quite literally. The universe, in this view, is a vast, ongoing computation. The laws of physics are its immutable operating code, and the passage of time is simply the clock cycle of this grand processor, ticking through one calculation after another. The evolution of galaxies, the fusion in stars, and the electrical impulses in your brain are all incredibly complex subroutines running on this ultimate machine. This informational lens connects to the simulation hypothesis, but in a far more fundamental way. A simulation is one specific kind of information processing, but the it-from-bit idea is more radical. It suggests that information is not just what a universe is made of in a simulation. It is what any universe must be made of at its most basic level. Whether base reality or a simulated one, the underlying currency is the same, bits and qubits, so we are left with a dizzying reflection. If reality is nothing more than a cosmic data stream, what are we? Are our minds, our memories, our very consciousness, just particularly sophisticated and self-referencing patterns of information processing, temporary eddies in an eternal flow of bits? This reduction of all things to pure information feels both alien and elegant, stripping away the solidity of the world to reveal a universe of pure, elegant thought. The abstract mathematics of string theory blossoms into a cosmic garden of almost infinite variety. This 21st journey invites us to wander through the landscape of string theory, a breathtaking vista of possible realities where the multiverse is not just a collection of bubbles, but a terrain of every conceivable physical law. The equations of string theory do not yield a single, unique solution. Instead, they offer a staggering number of valid, low-energy configurations known as vacuum states. Each of these states represents a self-consistent set of physical constants and laws, a potential universe with its own unique properties. The theoretical physicist Leonard Susskind aptly named this the landscape, describing it as a megaverse of possibilities. The sheer number of these possible vacua is beyond human comprehension, estimated to be 10 to the power of 500. That is a 1 followed by 500 zeros, a number so vast it exceeds the total count of atoms in our entire observable universe. Within this cosmic garden, our universe is simply one small valley, one particular arrangement where the constants allow for atoms, stars, and life to form. But a valley is not stable on its own. This is where the crucial process of moduli stabilization comes into play. In the early universe, scalar fields known as moduli determined the size and shape of the extra dimensions. For a universe to become stable and classical, these moduli must settle into specific, fixed values, a process that pins down the laws of physics as we know them. If they do not stabilize, the universe remains a chaotic quantum foam, unable to support any complex structure. This concept is deeply intertwined with the string theory swampland, a powerful and ongoing research program. The swampland is the set of effective field theories that look perfectly consistent on their own, but can never be completed into a full theory of quantum gravity within the framework of string theory. They are theories stranded in the swampland, forever disconnected from the consistent high ground of the landscape. A key conjecture suggests that in a consistent theory, the vacuum energy or dark energy cannot be arbitrarily small and positive and remain static. It must be able to decay, forcing the universe to evolve. This provides a potential, natural explanation for why we find ourselves in a universe with a small but non-zero cosmological constant. It is not a fixed, eternal parameter, but a temporary value on a slow roll toward a lower energy state. So we are confronted with a deeply existential question. If the landscape is real, with 10 to the 500 different possible universes, how did we end up in this one? The answer seems to be pure, blind chance, a cosmic lottery where our ticket happened to have the right numbers for life. But this immediately leads to a profound and difficult puzzle known as the measure problem in cosmology. In an eternally inflating multiverse producing an infinite number of bubble universes, how do we define probabilities? If every possible universe exists in infinite copies, how can we say that a life-friendly universe like ours is rare or likely? Any outcome that is possible will happen an infinite number of times. This makes the very notion of probability seem to break down, forcing us to ask not just why we are here, but how we can possibly calculate the odds of our own existence in an unbounded cosmos. Even in an infinite multiverse, not every possibility feels equally likely. This 20-second theoretical journey confronts a profound mathematical puzzle, the measure problem in cosmology, which asks how we can possibly calculate probabilities when every conceivable event happens an infinite number of times. As physicist Alex Vilenkin has pointed out, in an infinite universe, anything that can happen will happen an infinite number of times. This creates a crisis for meaning. If an infinite number of versions of you are doctors and an infinite number are painters, how can we say that becoming a doctor was ever a more or less probable outcome? The measure problem is the challenge of finding a sensible way to count observations, to weigh one infinity against another so that the concept of likelihood does not completely break down. Scientists have proposed various mathematical tools known as measures to cut this infinite knot. One approach is the pocket measure, which focuses on the individual bubble universes spawned by eternal inflation. It attempts to compare the relative volumes or numbers of these pockets, asking what fraction of them possess certain properties, like the correct cosmological constant for life. Another compelling idea is the causal diamond measure, which restricts the counting to the finite region of spacetime that can ever be in causal contact with a single observer. It essentially draws a boundary around the part of the multiverse you could ever possibly see or influence, ignoring the infinite, unreachable beyond. This method often avoids some of the more bizarre paradoxes that emerge from raw infinities. The most startling of these paradoxes is the Boltzmann brane problem. This thought experiment suggests that in an infinitely old and vast universe, random quantum fluctuations could, by sheer chance, spontaneously assemble a fully formed, conscious brain, complete with false memories of a past life floating in the void. In fact, in an eternal universe, such random assemblies would occur infinitely more often than the slow, gradual evolution of brains through biological processes. So, statistically, you should be a lone, disembodied Boltzmann brain hallucinating a world, rather than a real person living in a structured cosmos. The fact that we are not, that we observe a coherent and ordered universe, is a powerful clue that our cosmological models must be missing something crucial, perhaps a proper measure that discounts these random, freak observations. This entire struggle is deeply tied to anthropic reasoning. We are not random observers plucked from the cosmic void. We are observers who necessarily find ourselves in a rare region of the multiverse compatible with our existence. When we ask for the probability of our universe, we are really asking, given that we exist to ask the question, what should we expect to observe? A successful measure must explain why we observe a universe that is both old and large enough for life to evolve, rather than one that is just barely suitable, or one populated by fleeting phantom minds. So we are left to ponder a question that shakes the foundations of science and probability. If all outcomes are equally real in an infinite ensemble, what does it even mean for something to be likely or unlikely? Our intuition for chance forged in a finite world may be completely inadequate for the true, staggering scale of cosmic reality. This probabilistic quagmire forces us to question the very nature of our observations and the reliability of our own memories. A conscious mind could spontaneously blink into existence from the chaos of empty space. This is the 23rd theoretical journey, the deeply unsettling puzzle of Boltzmann branes. Named for the physicist Ludwig Boltzmann, these are not biological branes but self-aware entities that randomly assemble from quantum fluctuations in the vacuum. They would form complete with detailed but entirely false memories of a past life, a world, and an identity, only to dissolve back into the void an instant later. This bizarre idea arises directly from classical thermodynamics and the concept of Poincaré recurrence. This mathematical theorem states that in a system with a finite number of possible states, like a box of gas molecules, every possible configuration will eventually recur given enough time. In an infinitely old universe, even the most astronomically unlikely event, like all the air in your room suddenly rushing into one corner, is not just possible, it is guaranteed to happen an infinite number of times. The spontaneous formation of a fully conscious brain is just such an improbable configuration. In the context of eternal inflation and an infinite multiverse, this creates a devastating problem for probability. The random, spontaneous fluctuation of a single, disembodied brain is vastly more probable than the slow, gradual evolution of an entire, ordered cosmos with galaxies, stars, planets, and billions of biological observers. It requires far fewer particle interactions and far less time from a statistical standpoint. So, if our cosmological models are correct, Boltzmann branes should outnumber ordinary observers like us by an infinite factor. This leads to a terrifying question of epistemology. How can you be certain that you are not a Boltzmann brane, having just fluctuated into existence a moment ago with all your memories of childhood, your knowledge of physics, and your sense of self pre-installed? The world you perceive around you could be a complete fabrication, a detailed hallucination that will vanish as suddenly as it appeared. This puzzle is intimately tied to the arrow of time, the one-way direction from past to future that we all experience. The second law of thermodynamics, which states that entropy always increases, gives time its arrow. Our universe started in a state of incredibly low entropy, the highly ordered Big Bang, and has been evolving toward disorder ever since. This low entropy beginning is what makes the gradual, step-by-step evolution of life possible. A Boltzmann brane, however, is a product of a high entropy environment. It is a momentary, random decrease in disorder, a statistical fluke in a cosmos that is otherwise old, cold, and featureless. The fact that we observe a coherent, structured, low-entropy universe around us is powerful evidence that we are not Boltzmann branes. We are part of a long, continuous chain of causality stretching back to a definite beginning. Yet, the very fact that we must argue against this possibility highlights how deeply our understanding of cosmology is connected to the nature of observation itself. Does the eerie possibility of these phantom minds make you question the reliability of your own memories and experiences? This profound puzzle over the direction of time and the nature of observers forces us to consider if time itself could be an emergent property, born from a more fundamental, timeless reality. Time's relentless forward march is not a universal constant, but a local phenomenon. The 24th theoretical journey confronts the arrow of time and entropy, examining why we remember the past but not the future, and whether this flow could be reversed in other realms of the multiverse. Physicist Sean Carroll clarifies the core of this mystery, stating that the arrow of time comes from the low entropy of the early universe. Entropy is a measure of disorder, and the second law of thermodynamics dictates that the total entropy of an isolated system always increases over time. This is why an ice cube melts in a warm room, why a shattered glass does not spontaneously reassemble, and why you can remember yesterday but not tomorrow. The universe as a whole is moving from a state of exquisite order to one of ultimate disorder. Yet this law presents a profound puzzle. Why did the universe start in such an incredibly ordered, low-entropy state to begin with? This is known as the past hypothesis. The early cosmos was a hot, dense, and remarkably smooth soup, a configuration of fantastically low entropy that provided the initial winding of the cosmic clock, setting the direction for time's arrow. There is another, more subtle clue embedded in the laws of physics, a phenomenon known as CP violation. This describes a tiny asymmetry in the behavior of certain subatomic particles and their antimatter counterparts. The combined operations of charge conjugation, which swaps particles for antiparticles, and parity, which mirrors spatial coordinates, are not perfectly symmetrical. This minuscule breaking of symmetry, observed in the decay of particles called kaons, provides a fundamental microscopic basis for why time has a preferred direction. It suggests that the laws of physics themselves are not completely time-symmetric. Now, let your mind wander to a truly alien dimension. Imagine a universe that began in a state of maximum entropy, a featureless, high-disorder sea. In such a cosmos, the arrow of time would be reversed from our perspective. Beings there would perceive their past as our future. They would remember events we consider yet to happen, watching with anticipation as the cosmos becomes more ordered and structured, moving toward what we would call the Big Bang. For them, a broken cup would slowly gather itself from the floor and leap back onto the table, perfectly whole. This is not mere science fiction, but a physically consistent possibility within the equations. So we must ask, if entropy defines time's arrow, could alternate dimensions nestled in the wider multiverse experience entirely different temporal flows? Some pockets might be timeless, frozen in a single moment, while others could have cyclical time, or even multiple, branching temporal dimensions. This exploration of time's origin and direction weaves directly back into our earlier journeys on cyclic universes, where each new eon inherits a low entropy beginning from the evaporation of black holes in the previous cycle. Does this mean the flow of time itself is not a fundamental feature of reality, but an emergent property, a story that only makes sense within the specific thermal history of our own cosmic bubble? Space-time may be nothing more than a cosmic network of shifting relationships. The 25th theoretical journey, quantum graphity, proposes a reality where dimensions are not fundamental, but emergent properties that crystallize from a more basic, interconnected state. In this model, the universe begins not as a singularity, but as a perfect graph, a network where every single point is connected to every other point. In this initial state of maximum connectivity, the concepts of here and there are meaningless because everything is adjacent to everything else. There is no space, no distance, and no dimensionality in any form we would recognize. This is a background-independent approach to quantum gravity, meaning that space-time itself is not the fixed stage on which events play out. It is the main actor, a dynamic entity that evolves and changes. The birth of our familiar dimensions was a cosmic phase transition, a dramatic cooling that broke the perfect symmetry of this primordial graph. Think of it like water freezing into ice. The liquid water is uniform and symmetric, but as it freezes, it forms a crystalline structure with distinct properties and directions. In the same way as the early universe cooled from its hot, dense beginning, the perfectly connected graph underwent a phase transition. Countless connections were severed, and the network became sparse and ordered. It is from this new, frozen structure that the three spatial dimensions we move through today spontaneously emerged. The specific pattern of remaining connections defines the geometry of space itself. This process of dimensional emergence has profound physical consequences. In the early moments of the universe before the graph fully crystallized, the speed of light could have been vastly different. Light, in this model, is not a fundamental constant but a phenomenon that arises from the way information propagates across the network. If the connectivity of the graph was different, so too would be the maximum speed of causal influence. Furthermore, this model allows for the possibility of dimensional reduction at extremely high energies. If we could probe the universe at the Planck scale, spacetime might appear two-dimensional or even one-dimensional, as we begin to see the bare bones of the underlying graph before the illusion of higher dimensions takes hold. This forces a deeply foundational question. If dimensions are not fundamental, what is the true substance of reality beneath the stage of spacetime? Quantum gravity points toward pure information and relationship. The nodes of the graph are not things in space, they are the fundamental constituents, and the connections between them define what space even is. This view leads directly to theories of emergent gravity, where the force we experience as gravity is not a fundamental interaction, but a thermodynamic or entropic effect, a consequence of the way information is stored and processed on the cosmic graph. Could it be that gravity is simply the universe's way of responding to changes in its underlying information structure, a force born from the need to count its own connections? Gravity might not be a fundamental force of nature at all, but a side effect, an illusion born from the deep-seated tendency of the universe to descend into disorder. This 26th theoretical journey takes us into the world of emergent gravity, a radical proposal by physicist Eric Verland. He reimagines gravity not as one of the universe's basic ingredients, but as a phenomenon that emerges from the statistical behavior of something more fundamental. Much like the warmth of a fire is not a fundamental property, but emerges from the collective motion of countless molecules. Verland makes the stunning claim that gravity is a consequence of the universe's tendency to maximize entropy. In this view, what we perceive as the force of gravity is actually an entropic force, a result of systems evolving toward states of higher disorder. The central mechanism involves a concept called the holographic screen. Imagine that for any region of space, there is an imaginary two-dimensional surface containing all the information about the matter and energy within that volume. This screen acts like a boundary where information is stored, 1 bit per Planck area, as dictated by the holographic principle. Now, when a new particle approaches this screen, it effectively displaces some of the information, causing the screen to move outward to accommodate it. This displacement increases the entropy associated with the screen, and the natural tendency for entropy to increase is what manifests as an attractive force, pulling objects together. We interpret this statistical pull as gravity. A powerful example lies at the edge of a black hole. The immense gravitational force we associate with the event horizon is, in this entropic picture, simply the result of the universe's drive to maximize its entropy on that ultimate holographic screen. This perspective offers a breathtakingly simple explanation for one of cosmology's greatest mysteries, dark matter. In Verland's framework, the extra gravitational pull attributed to invisible dark matter halos around galaxies might not come from undiscovered particles. Instead, it could be an entropic effect. The ordinary visible matter in a galaxy alters the information content on the surrounding holographic screens, and this modification naturally produces an additional gravitational force that mimics the presence of unseen mass. The observed rotation curves of galaxies, which stay flat instead of falling off, could be a direct consequence of this emergent gravity, with no need for exotic particles. This idea is not just philosophical, it leads to testable predictions that differ from both Newtonian gravity and Einstein's general relativity. In the low acceleration environments at the outskirts of galaxies, entropic gravity predicts specific deviations. Scientists are now analyzing the distribution of matter in galaxy clusters and the gravitational lensing of light, searching for the unique signatures that would confirm gravity is indeed emergent. If these experiments bear fruit, it would revolutionize our understanding of the cosmos. So we are left with a profound question that echoes through our previous journeys on information. If gravity is not fundamental but emerges from entropy and information, does this finally dissolve the last great barrier to a theory of quantum gravity? It suggests that the search for gravitons, the quanta of gravity, might be a search for something that does not fundamentally exist, and that the true unification lies in understanding the quantum mechanics of information itself. The smooth, continuous fabric of spacetime may be a grand and convincing illusion. Causal Set Theory presents a universe built not from a flowing continuum, but from a discrete, shimmering dust of fundamental events. Each event is a single point in a vast cosmic set, and the only truly fundamental property connecting them is a simple binary relation, cause and effect. One event either precedes another or it does not. From this sparse, minimalist foundation, the entire richness of spacetime, its four-dimensional geometry, and even the force of gravity is meant to emerge. This approach to quantum gravity boldly strips away the assumption of continuity, focusing entirely on the causal relationships that define the history of the cosmos. The process of building a universe from this causal dust is often described as a cosmic sprinkling. Imagine taking a manifold, a smooth, continuous spacetime, and randomly sprinkling a finite number of points into it. The only rule is that you must respect the causal order, the light cone structure of that manifold. A point in the future can only connect to a point in its past. This sparse collection of points and their causal links is a causal set. The stunning revelation is that the original, smooth geometry of the manifold, its curvature and dimensionality, can be recovered or approximated from the pattern of connections in this sparse causal set. The geometry is not fundamental. It is a statistical collective property of the underlying causal network. To grasp the scale of this granularity, consider our Hubble volume, the entire observable universe. A causal set describing this region would contain a number of elements so vast it defies imagination, roughly 10 to the power of 240. Yet this number is still finite. Each of these fundamental events occupies a volume on the scale of the Planck length, the absolute smallest possible unit of space. This is the true grain size of reality, 1 billion times smaller than a proton. We can estimate the dimensionality of our universe by studying the pattern of connections within the causal set. In a four-dimensional spacetime, the number of causal links a given event has follows a specific mathematical pattern as you look deeper into its past. By analyzing these patterns within the causal set that represents our cosmos, we can, in principle, derive the fact that we live in 4 dimensions. It is a property that emerges from the relationships, not one that is built in from the start. Imagine a powerful computer simulation designed to explore this idea. You program it with the simple rules of Causal Set Theory, a random sprinkling of points with a defined causal structure. As the simulation runs, you watch as a stable, four-dimensional spacetime geometry crystallizes from the chaos of connections. You see galaxies and stars form not as objects in a pre-existing space, but as intricate, persistent patterns within the causal network itself. The simulation would be a dynamic proof that our entire cosmic history could be encoded in a vast, evolving graph of cause and effect. So, if spacetime is truly this granular, composed of a finite number of fundamental events, what does that imply about the flow of time? Is the seamless progression from one second to the next merely a macroscopic averaging of countless tiny, causal steps? This discrete, relational framework finds a powerful ally in another ambitious approach to quantum gravity, one that also weaves spacetime from a fabric of interconnected loops. Spacetime is not a smooth, continuous fabric, but a shimmering tapestry woven from a network of loops. This is the 28th theoretical journey, Loop Quantum Gravity, a framework that dares to quantize the very geometry of space and time. Its foundational structure is the spin network, a sprawling graph where the edges represent quantized threads of gravitational field, and the nodes are the elementary grains of volume where these threads intertwine. As the theory's co-founder Carlo Rovelli explains, space is made of grains of volume. The entire cosmos is a single dynamic network, a background independent structure that is not embedded in any pre-existing space, but which itself defines what space is. This approach stands in stark contrast to string theory, which requires a fixed spacetime stage for its strings to vibrate upon. Here, the stage itself is the main actor. The evolution of these spin networks is described by spin foam models. Imagine a stack of spin network snapshots, each one a single moment in time. A spin foam is the four-dimensional history that connects them, a frothy, quantum structure where spacetime itself becomes a collection of bubbles or foams, representing all the possible ways the geometry can change. This quantization leads to a profound physical prediction, the quantization of area and volume. Just as light comes in discrete packets called photons, space itself comes in indivisible units. There is a smallest possible area in the universe, the Planck area, and a smallest possible volume. You cannot have half a grain of space any more than you can have half a photon. This revolutionary idea provides a stunning solution to the black hole information paradox. In loop quantum gravity, the event horizon of a black hole is not a smooth surface. It is a patchwork of these tiny, quantized areas. The information about what fell into the black hole is not lost behind the horizon, but is encoded in the specific configuration of these microscopic area quanta on the surface, perfectly preserved. This allows the information to be slowly released as the black hole evaporates through Hawking radiation, resolving the paradox. This quantum geometry also reshapes our cosmic origin story. The Big Bang was likely not a true singularity of infinite density. Instead, loop quantum cosmology, a simplified application of these principles, suggests a big bounce. The immense gravitational pull of a collapsing universe is eventually counteracted by a powerful repulsive force generated by the quantum nature of geometry itself. The universe does not crush itself into nothingness but rebounds, giving birth to a new, expanding cosmos. Our entire universe could be the successor to a previous cosmic cycle. This leads to a deeply philosophical reflection. If space is quantized, composed of a finite number of tiny grains, can we ever truly speak of infinite divisibility? Is the ancient idea of cutting something in half forever finally at an end? the very concept of a mathematical point with zero size may have no physical reality. This granular perspective introduces the mind-bending concept of non-commutative spaces. In our everyday world, it does not matter if you measure the length of a table first and then its width, or the width first and then the length. The operations commute, meaning the order does not change the result, but at the Planck scale, in the quantum geometry of loop quantum gravity, this may no longer be true. Measuring the geometry of space in one direction could fundamentally disturb a measurement in another, implying that space at its core is a frenetic, uncertain place where precise locations become ambiguous. Your intuitive sense of a stable, predictable space is a magnificent approximation that only emerges when we average over its countless, jittering quantum grains. The very coordinates of space could lose their certainty at the smallest scales, creating a reality where the order of your measurements fundamentally changes the result. This is the 29th theoretical journey, Non-Commutative Geometry, a profound mathematical framework pioneered by Elaine Connes. In our everyday world, geometry is commutative. If you walk 5 steps north and then 10 steps east, you end up at the exact same spot as if you had walked 10 steps east first and then 5 steps north. The operations commute and the sequence does not matter, but in the quantum realm, this familiar rule breaks down. Non-commutative geometry proposes that space-time itself obeys this quantum principle. At the Planck scale, measuring the position of a point in one direction and then another might not yield the same result as performing the measurements in the reverse order. This leads to a fundamental fuzziness, a quantized and uncertain geometry where the very concept of a sharp, pinpoint location becomes meaningless. Think of it as an extension of Heisenberg's famous uncertainty principle, which states you cannot know both the exact position and momentum of a particle. Here, that uncertainty is applied to the fabric of spacetime. You cannot simultaneously specify all the geometric coordinates of an event with infinite precision. The stage itself has a built-in blur. The mathematical engine that drives this idea is known as a spectral triple. This is a powerful algebraic package that generalizes the notion of a geometric space. It consists of an algebra of functions which tells you what you can measure on the space, a Hilbert space which provides the state of the system, and a Dirac operator which encodes all the geometric information like distances and curvature. In classical geometry, you can reconstruct a manifold from the spectrum of its Dirac operator, much like you can identify a drum by the sound it makes. Non-commutative geometry uses this same spectral data to define spaces that are too fuzzy or singular to be described by classical points. One of the most stunning applications of this framework is its ability to derive the entire standard model of particle physics from pure geometry. Connes and his collaborators showed that the intricate dance of quarks, leptons, Higgs bosons, and gauge forces can be seen as the spectral geometry of a tiny, non-commutative space. The Higgs field, which gives other particles their mass, emerges naturally from the internal geometry of this fuzzy space. This suggests that the particles and forces we spend billions to smash together in colliders might ultimately be geometric vibrations in a space where left and right no longer commute. In string theory, non-commutativity arises when strings move in backgrounds with specific fields turned on. The endpoints of open strings become fuzzy, and the space-time coordinates these strings probe are themselves non-commuting. This creates a rich, non-local geometry that string theorists explore to understand the deep structure of reality. So we are left with a profound question about the nature of knowledge itself. If space-time is fundamentally non-commutative, imposing a limit on how precisely we can ever measure it, does this represent an ultimate barrier to our understanding of the cosmos? This algebraic view of reality, where geometry is derived from abstract relationships, compels us to confront the final frontier, the nature of the void from which everything emerged. The void of space is not truly empty, but a seething ocean of potential. This 30th and final theoretical journey takes us to the quantum vacuum, a state of pure nothingness that is paradoxically alive with activity. According to quantum field theory, what we perceive as empty space is the lowest possible energy state, yet it is constantly fluctuating. This zero-point energy is the reason empty space can never be perfectly still. At the tiniest scales and over the briefest moments, pairs of virtual particles and their antiparticles spontaneously blink into existence, borrowing energy from the vacuum before annihilating each other almost instantly to repay the debt. This endless, frothing dance is not just a mathematical curiosity, it has observable consequences. The Casimir effect provides a stunning demonstration. Imagine two uncharged, perfectly smooth metal plates placed incredibly close together in a vacuum. The space between the plates is so narrow that only certain wavelengths of virtual particles can appear there, while outside the plates, a wider spectrum of fluctuations is possible. This difference in pressure creates a tiny but measurable force that pushes the plates together, a direct signature of the quantum vacuum's relentless energy. Physicist Lawrence Krauss has taken this idea to its ultimate conclusion, exploring the concept of a universe from nothing. He argues that if the total energy of the universe is zero, with positive energy in matter and radiation perfectly balanced by the negative energy of gravity, then our entire cosmos could have arisen from a random quantum fluctuation in a pre-existing void. No violation of conservation laws, no divine spark, just the inevitable outcome of quantum mechanics playing out on a cosmic scale. This leads to the possibility of vacuum decay, a truly apocalyptic scenario for our universe. Our vacuum might not be the true, lowest energy vacuum, but a false one, temporarily stable like a ball resting in a small dip on a hillside. A quantum fluctuation could tunnel through the energy barrier, creating a bubble of true vacuum that expands at the speed of light. This bubble wall would rewrite the laws of physics as it moved, dissolving atoms and ending the universe as we know it in an instant. This profound power of the vacuum is also the source of one of physics' greatest embarrassments, the cosmological constant problem. When physicists try to calculate the vacuum energy's contribution to dark energy, the result is wrong by a factor of 10 to the power of 120. It is the worst prediction in the history of science, a glaring sign that we are missing something fundamental. One potential path forward is a theory called unimodular gravity, a modification of Einstein's general relativity that restricts the possible solutions for the cosmological constant, potentially explaining why it is so small but not zero. Could our entire universe be a single, spectacular virtual particle, a baby universe born from a quantum fluctuation in the bulk of a higher dimensional multiverse? In this view, the Big Bang was not a unique event, but a common occurrence in the greater metacosmos, so we are left with the most profound question of all. If our entire reality can emerge from the restless quantum nothingness, what does that imply about the ultimate origin of the multiverse itself? Does the infinite chain of causation simply extend backward forever, an endless regression of cosmic seeds sprouting from greater voids, or does the very concept of a beginning finally lose all meaning in the face of such eternal, creative emptiness? These 30 journeys are not isolated paths, but a single, intricate map of a layered multiverse. When we step back, we see how the holographic principle, where our three-dimensional world is projected from a two-dimensional surface, finds a profound echo in the mathematical universe hypothesis. Both suggest that the tangible solidity we experience is an emergent property, a consequence of deeper, more abstract rules. The quantum foam at the Planck scale could be the raw material from which the orderly dimensions of loop quantum gravity crystallize, while the endless branching of the many worlds interpretation might be the very mechanism by which the vast landscape of string theory is explored. Even the simulation hypothesis aligns, portraying a cosmos where the fundamental currency is not matter but information, perfectly mirroring the it from bit philosophy. Physicist David Deutsch champions this kind of integrated thinking, arguing for a fabric of reality woven from the intertwining strands of quantum physics, epistemology, computation, and evolution. These theories are not mutually exclusive, they are different vantage points on the same staggering truth. Imagine a multidimensional diagram where each journey is a luminous thread. The thread of the Brane Multiverse weaves directly into the Ekpyrotic cycle, where colliding membranes ignite new cosmic eons. The thread of Emergent Gravity connects to Causal Set Theory, both suggesting that spacetime is not fundamental but a collective behavior of something more basic. Consciousness, as explored in the von Neumann-Wigner interpretation, becomes the mysterious process through which a single path is selected from the quantum tapestry, giving a unique, subjective reality to one thread in the infinite weave. The role of mathematics is the universal language that describes this entire structure, while information is the substance from which it is all made. So how does this integrated view, this unified multiverse framework, change your daily perception of reality? Does the cup of coffee in your hand feel more real, knowing its existence is supported by such a deep and interconnected cosmic architecture, or more dreamlike, understanding it is one manifestation in an infinite ensemble of possibilities? This synthesis of journeys reveals a cosmos of breathtaking depth and coherence, preparing us to ask the final, most personal question of all. Our voyage through 30 cosmic doorways reveals a multiverse not of a single type, but a breathtaking ecosystem of possibilities. We have wandered from the branching paths of quantum choice to the holographic projection of our reality, from the cyclic rebirth of eons to the digital code of a potential simulation. This grand tapestry weaves together threads of geometry, information, and consciousness, each theory a unique lens on the same profound mystery. The diversity of these models is not a sign of confusion, but a testament to the creative power of science to explore the ultimate frontiers of what might be real. A crucial thread running through many of these journeys is the active role of the observer. From the conscious collapse of the wave function to the anthropic selection of a life-friendly universe, our act of looking and questioning seems inextricably linked to the reality we find ourselves in. This points toward a potential unification of physics, a long-sought theory of everything that might finally reconcile the quantum realm with cosmic gravity, revealing the underlying principles from which all these dazzling possibilities spring. As physicist Brian Greene once reflected, the multiverse may be the most radical idea in science. It fundamentally challenges our most basic assumptions about existence and identity. If countless versions of you are living out every possible life, what becomes of the singular self you feel so deeply? If the entire cosmos is a mathematical structure, are your thoughts and feelings just equations being solved? These are not just abstract puzzles for physicists, they are deeply personal questions that touch the core of your own life. How does this knowledge reshape your feelings about the choices you have made or the path that lies ahead? Does it instill a sense of boundless freedom or a curious weightlessness? I invite you to reflect on which of these 30 journeys shifted your perspective the most. Did the cosmic bread of the Brane Multiverse capture your imagination, or was it the timeless stillness of the block universe that left you in quiet contemplation? Share your thoughts in the comments below and let us continue this conversation. If this exploration has expanded your horizons, consider subscribing for more deep dives into the mysteries of space and existence. The universe is vast beyond measure, but our shared curiosity is the one force that can truly make it